Yeah, thank you very much, Hamanaka-san. So it was a surprise for me then when I was approached by Hamanaka-san about this talk, because actually, although pluri-Lagrangian systems is a pretty recent development, I already somehow left this area and did not actively work on pluri-Lagrangian systems for a couple of years. But nevertheless, I think there have been some development which is worth disseminating more widely, and this is a very good possibility, very good opportunity to do this. The talk will be based on several older papers by myself, because, as I said, there have been no quite recent work, but I think they are not very well known and might be interesting. Maybe just a couple of introductory words. So the pluri-Lagrangian theory is the theory of integrability in the Lagrangian context. Usually integrability is formulated in the Hamiltonian context in physics, and the standard notion of integrability is the Liouville integrability, which means the existence of sufficiently many commuting flows. And the pluri-Lagrangian theory is an attempt to give the interpretation of this purely on the Lagrangian side, so in terms of configuration space and not of the phase space. So we do not have a priori symplectic structure or something like this, but we are only dealing with variational problems. And the pioneering work in pluri-Lagrangian systems has been done by Frank Nijhoff in Leeds. So the very first paper by him and Sarah Lobb was 2008, I think. It was the starting point of the whole theory. And as it has been done in discrete systems. And the most natural, actually, and beautiful formulation of everything in pluri-Lagrangian stuff is given in context of discrete systems, which is also my main topic. But again, today there will be not a single word about discrete systems. Everything will be for continuous systems, for ordinary differential equations and partial differential equations. Maybe on the level of discrete systems, pluri-Lagrangian stuff could be better understood because it is less technical. So the continuous theory will be pretty technical. There will be pretty many technical details, and I apologize for that because there are technical computations along the way which are necessary to understand things. But on the other hand, the majority of people do not work with discrete systems. I appreciate that most of the people work with continuous systems, and therefore this might be more useful for everybody. So maybe one last word. So the pluri-Lagrangian theory has been mainly developed at two points on the Earth. One is Leeds, where Professor Nijhoff has or had a group. He's now retired, but the group is still active. And they developed the theory under a different name, under the name of Lagrangian multiforms. And another point is Berlin, where I had several students occupied with this topic, and we use the term pluri-Lagrangian systems. So pluri means many or several, and it was chosen this term just in order to avoid something like multi-Lagrangian or poly-Lagrangian, because all these terms have different meanings. So it has been chosen a term which was not used before. And moreover, another justification is the relation to the theory of pluri-harmonic functions. So it turns out that pluri-Lagrangian systems in the linear case are very closely related to the so-called pluri-harmonic functions, but this topic is also not mentioned today. So let me now pass so what is, yeah, pass to the exposition. It will be consisting of two parts. One is one-dimensional in the sense that we are dealing with ordinary differential equations, or maybe with differential equations from classical mechanics. and will be based on these two papers. And the part 2 will be for partial differential equations, actually for two-dimensional partial differential equations with two-dimensional space-time. So let me start just with the formulation of one-dimensional pluri-Lagrangian problem. So I will not give you any motivation for a while, but it turns out that all the theory, which is pretty unusual, it has nevertheless relations with very classical stuff like Noether theorem and Noether variational symmetries. So we are dealing with Lagrangian problems. That means that we look for critical points of functionals, and moreover, the functionals depend on a field, which can be anything, which can take values in some manifold, or in our case, it will be just an n-dimensional vector space, and on its derivatives, first-order derivatives. So it will be first-order theory. So Lagrangian depends on the field and its derivative, but the field depends not on one time, but on many times, on m times. M is the number of times in this theory, and it corresponds somehow to the number of commuting flows, as we will see. Now we are integrating over curves, integrating one forms. So that means that we start with a one form, which depends, each coefficient of this one form in the m-dimensional space depends on the field and its first-order partial derivatives. So these u will be placeholders for first-order partial derivatives with respect to the time number 1, number 2 to number m. So we integrate this one form along any curve in multi-time. So we consider any smooth curve in multi-time, fix 2 points, prescribe the values of fields at these 2 points, connect them by an arbitrary curve, and integrate the Lagrange one form along arbitrary curve. And then we require that the solution for our problem delivers critical points to all these functionals irrespectively of the curve. So that means that we can vary not only the field x, but also the curve in the multi-time. Now it is a very unusual formulation because, as you probably remember, in standard Lagrangian mechanics, we are just dealing with one-dimensional time, and we integrate the Lagrange function depending on x and its first derivative. I will come to this in a couple of minutes. And then one has Euler-Lagrange equations as necessary conditions for the critical points. The first question is, what are the equations coming to replace the standard classical Euler-Lagrange equations? And here is the answer. So a field x, which delivers a critical point for this action functional for arbitrary smooth curve gamma connecting to given points, satisfies the following so-called multi-time Euler-Lagrange equations. So here are the equations. If you differentiate any coefficient of the one form with respect to velocity with respect to a different time, so k and l are different, then the result should vanish on solutions. However, if you differentiate any coefficient with respect to its own velocity, so you differentiate L1 with respect to derivative in time t1, Lm with respect to derivative in time tm, then all these quantities should be equal to one another from 1 to m. And we call the common value of all these quantities by p. It is the analog of the canonically conjugate momentum in this theory. And then for all times from 1 to m, the partial derivative of this canonically conjugate momentum with respect to the time is equal to the partial derivative with respect to x itself of the kth component of the one form. So you see, instead of one Euler-Lagrange equation, which would be this one in the case m equal to 1, we have a huge system of equations, and all of them have to be satisfied. That means that if you start with arbitrary coefficients L1 to Lm, you will get something highly overdetermined, which does not possess general solutions. So there will be contradictions. And this corresponds to the fact that integrable systems are rare. So not an arbitrary pluri-Lagrangian one form admits solutions, but only integrable systems come into play here. So one can think about the situation when this system of Euler-Lagrange equations is consistent as the case of integrability. One important property is automatically built into this theory, namely on solutions of multi-time Euler-Lagrange equations, the one form is almost closed. Almost closed is that its exterior derivative is constant. It might be equal to 0 for any two pairs of times k and L, and this is the usual case. But actually, the more general case, which requires no extra work, is that the exterior derivative, so these are the coefficients of the exterior derivative of the one form L, are constant on solutions. So if all these constants are equal to 0, then the pluri-Lagrangian one form is closed on solutions of multi-time Euler-Lagrange equations. And that means that the critical value of the functional does not depend on the choice of the curve connecting to given points in multi-time. So let me give you just one example. It is the famous Toda chain. And I will give you a formulation, a pluri-Lagrangian formulation with just two times. So it will describe the Toda chain and its first commuting flow. And here is the coefficient by dt1. And here you can recognize just the standard Lagrangian of the Toda chain. So it is kinetic energy minus potential energy exponential. And how one comes to this second result is one of the main goals of this topic. I will tell you this. One checks that the multi-time Euler-Lagrange equations are satisfied. In particular, let me show you how the first equations are satisfied. So the partial derivative of the first coefficient of the first Lagrangian with respect to the second derivatives is equal to 0, as it should, because this L1 does not depend on velocities with respect to T2. And when we require that the partial derivative of L2 with respect to the time T1 equals to 0, this gives us something non-trivial, namely these differential equations. So the derivatives of the field xi with respect to the time T2 should be given by these formulas. And this is a very famous thing. It is the so-called commuting flow with the, for the Toda system, but I will come to this again in a couple of minutes. Then the partial derivatives of coefficients with respect to their own velocities are obviously equal, because they are equal to the first time partial derivative, which is the canonically conjugate momentum. And then we get those two equations from the third group of multi-time Euler-Lagrange equations. And the first line gives you the usual equations of motion for the Toda chain. And the second line is actually nothing but a differential consequence of this formula. If you differentiate this formula with respect to T1, you will get nothing but the right-hand side of this equation. Therefore, we can say that the multi-time Euler-Lagrange equations for this one form with these coefficients by dt1 and dt2 consists of two equations. First of them being the Lagrangian form of the Toda chain, and second one is this evolutionary equation. By the way, it is not a very usual thing that variational problems, Lagrangian problems, provide you with first-order differential equations with evolutionary equations. But here we see that this evolutionary equation is just a part of the big system of multi-time Euler-Lagrange equations. Now I will return to the classical Lagrangian mechanics and to the very classical development in it due to Emmy Noether. So this slide is definitely very well known to everybody, to students in mechanics. So you start with a one-dimensional time with a configurational space and with a Lagrange function on the tangent bundle to the configuration space, or in other words, in case when this is just a vector space, this vector space is for positions and this vector space is for velocities. Then the principle of the least action is the standard one. You just integrate the Lagrange function along curves connecting two fixed endpoints, and you integrate just over an interval of the real axis. And these are the Euler-Lagrange equations. They are expressed in terms of the so-called variational derivatives. Variational derivative in this first order situation is just dl over dx minus the full derivative with respect to time of dl over dx dot. And the resulting expression, Euler-Lagrange expression, depends on derivatives up to the order 2, so that this is the system of second order differential equations. Passing to the Emmy Noether's development, so the first invention by Emmy Noether was actually the notion of a generalized vector field. This is a vector field, the analog of a vector field whose coefficients do not only depend on the point of the base configurational space, but also on derivatives. So a geometric meaning of those generalized vector fields are delicate. I wouldn't like to go into this detail, but one can think of this just as a first order differential operators on acting on functions of x with coefficients which depend on x and x dot. And the n-tuple of coefficients of this vector field is called characteristic of the vector field. Once again, its component depend on the coordinates of the tangent bundle, so on x and x dot. We can prolongate the action of such a vector field by letting it act on differential polynomials of x, so on functions which depend not only on x itself, but also on first order, second order derivatives, and arbitrary order derivatives. And the prolongation is obtained in a natural way. So if you differentiate with respect to x, you have to multiply the corresponding component by the component of characteristic. If you differentiate with respect to the velocity, you have to multiply with the full derivative of the characteristic with respect to time, and so on. If you differentiate with respect to the second order derivative, you have to multiply with the full derivative of the second order of VI, and so on. So this is the rule how this differential operator acts on arbitrary degree differential polynomial of x, meaning anything depending on x and its arbitrary order derivatives in time. The definition of a variational derivative of a variational symmetry of Emmy Noether is the following one. So the classical definition of the symmetry would be just vanishing of the Lagrange function with respect to corresponding derivative. But what Noether required was not vanishing of the Lagrange function, but vanishing of the variational of the action and the variation of the integral of L. And this remains 0 if the derivative of the Lagrange function with respect to the corresponding generalized vector field is just a full time derivative of anything. So this anything is called the flux of the variational symmetry. So this equation So on the left-hand side, you differentiate the Lagrange function with respect to the generalized vector field. Then this must be a full time derivative of something of the flux of the variational symmetry. And another notion which is necessary to formulate the famous Noether theorem is the integral of the Euler-Lagrange equations. So these are the Euler-Lagrange equations for the Lagrange function L. And the function is called integral. And here again, we have something which deviates from the standard classical definition of the integral. Standard definition of the integral would be just time derivative of this function vanishes. Here it is not required that it vanishes, but it is required that it vanishes identically, but it is required that it vanishes on solutions of the Euler-Lagrange equations. And the way it is achieved is that this derivative is a linear combination of the Euler-Lagrange equations. So here are the Euler-Lagrange expressions, EI. These are variational derivatives of the Lagrange function with respect to xi. And we require that the full time derivative of this function is a combination of Euler-Lagrange expressions with the coefficients. And these coefficients are called, again, the characteristic of the integral of the Euler-Lagrange equations. Now, the famous Noether theorem. Every variational symmetry produces an integral with the same characteristic. And here is the explicit formula. You start with the variational symmetry of the Lagrange function L with the flux F. Then this function obtained by the combination of Lagrange function, its derivative with respect to velocities, and the characteristic of the variational symmetry and the flux of the variational symmetry, they claim that this function is an integral of Euler-Lagrange equations. And this is actually if and only if statement, because if you start with an integral of the Euler-Lagrange equation with a given characteristic, then the generalized symmetry with this same characteristic is a variational symmetry. And the flux is given by reading the previous formula from right to left. So F is given by this function minus J. So the usual formulation of the Noether's theorem is that integrals are in one-to-one correspondence to variational symmetries. And here is the precise formulation due actually to Noether from the paper, which is slightly more than 100 years old by now. I would even like to provide you with a very quick proof of Noether theorem in this formulation. It is obtained from a remarkable Noether's identity. And the Noether's identity tells you that if you start with an arbitrary function L, then it's the action of the generalized vector field on this function L minus this linear combination of Euler-Lagrange expressions is a full derivative of something. And this something is nothing but the function which you recognize in the formulas of the previous slide. This is the function A. So this is an identity which is verified by a straightforward computation, which I will sketch on the next slide. But if you have this result, then the Noether is immediate, because vanishing of this, so the fact that this expression is a full-time derivative, or the fact that this expression is a full-time derivative, are equivalent to one another, provided that J and F are related by this. So if you have F, then you have an integral J, and if you have an integral J, then you have a flux F for a variational symmetry. So the whole proof actually reduces to this algebraic statement that this combination is a full derivative of something. And here is the corresponding computation. It is nothing but the integration of by parts, or if you like, the product formula, the Leibniz formula for the differentiation or derivation of the product. So if you compute the derivative of the Lagrange function upon the action of the vector field V, and you take a linear combination of Euler-Lagrange expressions with the coefficients v. Then the first terms cancel away, and the remaining terms are just a full derivative of this. So that's all. The Noether theorem for the one-dimensional systems in classical mechanics is actually very easy to prove, even if it is not usually done in textbooks. But it is a very famous result, and I think it is less appreciated even in the modern textbooks on Lagrangian mechanics. And in order that you see how general it is, let me give you a couple of comments on the Hamiltonian side of the theory of the picture. So if you start just with the usual Lagrangian system and perform a Legendre transformation, which is a local isomorphism between the tangent bundle with coordinates x and x dot, and the cotangent bundle with the coordinates x and conjugate momenta, given by this standard formula, which you have actually seen in the multi-time formulation already. Then if the Legendre transformation is non-degenerate in the sense that the Hesse matrix of the Lagrangian with respect to velocities is non-degenerate, determinant is not equal to 0, then we have a local diffeomorphism fiber-wise between tangent bundle and cotangent bundle, between configuration space with velocities and the phase space. And in order to obtain the first order differential equations on the cotangent bundle, one performs the so-called Legendre transformation of the Lagrange function. So this is the standard formula. In this formula, you have to replace x dot by its expressions through positions and momenta, which is possible to do due to non-degeneracy condition. You get the Hamilton function, and then the trajectories are described by the standard Hamilton equations with this Hamilton function. Now let us see what the Noether's theorem gives us on this Hamiltonian side. If you start with the variational symmetry of the Lagrange function with a given characteristic and a given flux, then you have a Noether integral J. If in this Noether integral J, you express again velocities in terms of positions and momenta, then you get some function in terms of x and p. The claim is that this function Poisson commutes with h, or in other words, h1 is an integral of motion of the Hamiltonian system with the Hamilton function h. But this can be also inverted, which is much less known in the literature. Actually, if you start with any integral of motion, let us say with a function whose Poisson bracket with h vanishes, is equal to 0. And in this function, you express momenta through positions and velocities according to the Legendre transformation. Then you get function j, which depends on positions and velocities. And the derivatives of the integral h1 with respect to momenta under the same procedure will give you an n-tuple of functions depending on positions and velocities. Then these things define a generalized vector field, which is a variational symmetry of the original Lagrangian, and this thing will be a Noether integral of this generalized vector field. So actually, integrals of motion of a given Hamiltonian system are also in one-to-one correspondence with generalized symmetries of the corresponding Lagrange function. So this is really a full cover of the picture of integrability in the Hamiltonian context on the Lagrange side. So everything which commutes with Hamilton function h can be translated to the Lagrange side and gives you a generalized symmetry, a Noether symmetry of the corresponding Lagrangian. It is important that integrability on the Hamiltonian side is related to the fact that the system not only has many integrals of motion, but these integrals of motion Poisson commute among themselves. So this is the Liouville definition of integrability. And also this turns out to translate to the Lagrangian context. So assume that you have two variational symmetries, say V1 and V2, with the corresponding characteristics V1 and V2, and with corresponding fluxes F1 and F2. Then one can show that the commutator of the corresponding differential operators is given by the commutator of the corresponding generalized vector fields. So this is defined by the standard definition of the commutator on the vector fields, and then extended to higher order jets, so to differentiation with respect to all possible time derivatives. And then a natural definition of commutativity of variational symmetries is this. Two variational symmetries commute if the coefficients of their commutator vanish on Euler-Lagrange equations. And vanishing on Euler-Lagrange equations is again interpreted as being linearly expressed in terms of Euler-Lagrange variational derivatives. So on solutions of Euler-Lagrange equations, or on shell, as one says, these two vector fields commute. So they do not have to commute identically, so as just functions on configuration space, but only on solutions. And if this is the case, then one can prove the following theorem describing the commutativity on the Lagrange side. So if you start with two variational symmetries for a given Lagrange function with two fluxes and the two corresponding Noether integrals, then in case of commutativity of the corresponding variational symmetries, the fluxes satisfy this relation identically. This is the algebraic identity, but on solutions of the Euler-Lagrange equation, we know that this vanishes, and therefore these expressions are constant. And of course, if you translate the corresponding Noether integrals to integrals on the Hamiltonian side, according to the procedure which I described already, then the Poisson bracket of those two integrals is constant again, which, by the way, also means that the flows of the corresponding Hamilton functions commute. So the flows commute not only when the Poisson bracket vanishes, but also when the Poisson bracket is a constant. So the most important thing in this description is now related to the pluri-Lagrangian theory, to the multi-time one form. And in order to observe this, let me change the point of view slightly from algebraic to geometric. Until now, we considered the generalized vector fields as a differential operator acting on polynomials of the function x of a single time t. So we described the corresponding operators in terms of derivatives of the function x with respect to the time t. Now suppose that your Lagrange function admits m pairwise commuting variational symmetries. Now we interpret them as flows, as evolutionary equations. So now we for each generalized vector field. So vector fields are actually the right-hand sides of differential equations usually in science, and this is exactly how we interpret the things now. So we take the characteristics of the generalized vector fields and consider differential equations with these right-hand sides. These differential equations are with respect, each one with respect to own time, and the right-hand side on x and the time derivatives with respect to the time t. So those times t1 to tm are different from the time differentiation from with respect to which is denoted by the dot. And now the fact that the variational symmetries commute on solutions means that all these flows commute on the set of solutions of Euler-Lagrange equations. And this allows us to introduce functions of multi-times, of the time t, original time t, and of the times of all these m commuting flows. So now we consider functions not of one time, but of m plus one times. And the operator of generalized vector field is now just replaced by the operator of full differentiation with respect to the time number k. So this is the standard definition of the full differentiation with respect to time. And what is written here are the higher order partial derivatives of the configuration space coordinates of the coordinates xi with respect to the times given by the corresponding multi-index. So this is differentiation of xi with respect to t naught I naught times, with respect to t1 I1 times, and so on with respect to tm im times. So this is just the standard differentiation operator. Now let us try to consider the formulas which we have from this new point of view, from geometric point of view. This is the definition of the variational symmetry. So the derivative of the Lagrange function with respect to the time number k, which corresponds more or less to the generalized vector field number k, is a full derivative of something of the flux number k with respect to the time number 0. The commutativity of symmetries on shell, on solutions of Euler-Lagrange equations, then takes this form. The partial derivative of the flux number L with respect to the time number k minus the full derivative of the flux number k with respect to the time number L is constant depending maybe on k and L, and a good situation would be if those constants are equal to 0. Now what we see here, this set of relations, is nothing but the set of relations for the coefficients of the exterior derivative of the one form L with those coefficients. We now define a one form on this multi-time, on the time of dimension m plus 1, so the standard time and the times number 1 to m, the times of the flows 1 to m, with the coefficients which are just the standard Lagrange function and the fluxes of all the generalized symmetries. This looks very much like the pluri-Lagrangian one form. Unfortunately, it is not. So if we start just with this one form, where all the coefficients only depend on x and its time derivative with respect to t naught, with respect to t, then this is not a valid pluri-Lagrangian system because the multi-time equations are not consistent. In particular, if you differentiate any coefficient fk with respect to its own derivative, then it is equal to 0 for all k's from 1 to m, because the coefficients do not depend on x I t k. They only depend on x and x dot. And therefore, this 0 is not equal to the derivative of the first coefficient with its own derivative. So I remind you that the second group of equations of multi-time Euler-Lagrange equations was that all derivatives of all coefficients with respect to their own time derivatives should be equal. Here they are not. Therefore, even if this one form is very suggestive, it is not a valid one form for a pluri-Lagrangian system. but this disappointing result is very easy to repair. Namely, one has to perform adjustments in those coefficients times number 1 to m in order for them to involve those derivatives xi tk, but in a way which does not change them on solutions. So the corresponding theorem, which I give you, of course, on without proof, because it is a complicated computation, more or less complicated computation, is the following one. The right definition of the coefficients L1 to Lm in the pluri-Lagrangian system is obtained by changing the flux Fk by this expression, which is a combination of just the flows. So it vanishes on the flows if we consider the time derivative of xi with respect to the time tk and subtract the characteristic of the corresponding vector field, or one can just say that it is a linear expression with respect to derivative of x with respect to its own time tk with those coefficients. Then the claim is that for this one form, the system of multi-time pluri-Lagrangian Euler-Lagrange equations is consistent and moreover is equivalent to the Euler-Lagrange equations themselves, coupled with the commuting flows. And as I said, this modification does not change the form of the previous slide on shell, on solutions. So this is the end of the one-dimensional classical mechanical story. If you have any questions, maybe it would be a good time to ask, because now I'm going to pass to the two-dimensional systems, to variational symmetries for PDEs. So looks like there are no questions. Then let me pass to the two-dimensional theory. It is based on another pair of papers of myself with my postdoc, then Math-Phys, who moved to Leeds after that, and now I think he's in Kent. So this is devoted to to partial differential equations with two-dimensional spacetime, which will correspond to two-dimensional forms which we integrate, and this will be scalar equations. So the field will be denoted by u, and it is just a scalar function. So multi-time two form. I just now anticipate the full picture again without giving you motivation, and some part of motivation is coming from the Noether theory, which I will explain later. But by now we just start with a two form on a multidimensional space-time. So M again is the number of space-time coordinates. I denote them all by T1 to Tm, but actually one of them will play the role of space coordinate later. And the coefficients of a two form depend on anything, which means on u and its arbitrary ordered partial derivatives. First order partial derivatives, second order partial derivatives, and so on. So now the dimension in configuration space is just one. So the fields are scalar, but now we allow not only first order derivatives with respect to times, but arbitrary order derivatives. And then the two-dimensional pluri-Lagrangian problem consists in finding solutions for which deliver critical points to functionals obtained by integrating this two form over any smooth two-dimensional surface. Once again, it is a very unusual and uncommon setting in mathematics, because usually in the standard Lagrangian theory you integrate over you integrate a volume form. So for a two-dimensional system you integrate over a plane, For a one-dimensional system, you integrate over an integral of time and so on. And now you are allowed to integrate over an arbitrary two-dimensional surface in a multi-dimensional space. And you fix a boundary of this surface and ask for the differential equations which describe critical points of such systems. Again, now I give you just the result for those so-called multi-time Euler-Lagrange equation for two-dimensional partial differential equations. They look complicated and will be difficult to grasp, to understand just immediately in the framework of this talk. If you are really interested, you should look at them carefully afterwards. But again, this system of equations consists of three groups of differential equations. First of all, each coefficient Lij, when one computes the variational derivative in the plane ij with respect to derivatives of u with respect to other times. So multi-index k does not contain times number I and j. Then the result should be equal to 0. If you compute variational derivatives of Lij with respect to the indices which only contain I once, then the corresponding derivatives do not depend on j. So if you fix some number I and differentiate with respect to the multi-indices containing I, then the result is the same whether you compute this for j, ij, or ik. So all these things are equal to one another. This comes actually from considering, so to say, corners consisting of two planes intersecting along the direction number I. And when you consider three-dimensional corners spanned by times number I, j, and k, then, I'm sorry, the result should be equal to 0 here. So it is omitted. The sum of these three variational derivatives should be equal to 0. The definition of the variational derivative is standard one. You compute the partial derivatives and their full derivatives with respect to times ti and tj, the respective number of times. Okay, once again, to write this Euler-Lagrange equation is already a complicated task. To understand them is not very easy. But what one sees anyway, this is a huge system of partial differential equations, and it is not at all, again, guaranteed that it will be compatible. And for a generic choice of coefficients Lij, it will be not compatible, of course. And the situation when all these partial differential equations are consistent corresponds to integrability of the partial differential equations, as I will explain now. Let me give you just an example, just in order that you see how it works, how it is computed. Namely, I will give you a pluri-Lagrangian 2 form for a system which consists of a sine-Gordon equation. This is a famous sine-Gordon equation. It is a two-dimensional equation for PDE in a two-dimensional space-time. X and Y are the corresponding independent variables. And this sine-Gordon equation can be coupled with the so-called potential modified KdV equation. Here is the corresponding equation. So T is a new time. So this is also a two-dimensional PDE. It is also an integrable two-dimensional PDE in the space-time, space coordinate x, time coordinate t. Now I will show you that everything can be put into the three-dimensional time. Three-dimensional space-time with coordinates t1x, t2y, and t3t. So we consider the following two forms in this three-dimensional time with components L12 by dx wedge dy, L13 by dx wedge dt, and L23 by dy wedge dt. These are the coefficients L12, L13, and L23. So you can observe that so L12 depends on the partial derivative of u with respect to the times 1 and 2. L13 depends on the partial derivatives of u with respect to times number 1 and 3. And L23 depends on the partial derivatives of u with respect to times 2 and 3. And actually with respect to the time 1 as well, with respect to all 3 times. So derivatives with respect to x, y, and t appear in this term L23. And when we compute the multi-time Euler-Lagrange equations, it turns out to be equivalent to exactly the system I mentioned, consisting of the sine-Gordon equation and potential MKdV. And here is how it computes. So if you compute the variational derivative of L12 of the standard Lagrangian, by the way, this function is the standard Lagrangian for the sine-Gordon equation from the standard Lagrangian theory. If you compute its variational derivative in the plane 1, 2 with respect to u, you will get, of course, the same classical Euler-Lagrange equation. But also, if you compute the variational derivative of the coefficient 2, 3 with respect to derivatives u in the direction x twice, then vanishing of this variational derivative also computes to the sine-Gordon equation. So the sine-Gordon equation appears actually as two different multi-time Euler-Lagrange equations. The potential MKdV appears from the variational derivative of the coefficient 1, 3 with respect to ux. And as it should, it is equal to the variational derivative of L2, 3 with respect to uy. This is one of the second group of PDEs. And this is exactly this evolutionary equation. So we see again that this multi-time Euler-Lagrange equation can produce evolutionary equations, not only second-order equations, but also the first-order equations in some variables. And then there appear also non-trivial Euler-Lagrange equations among this huge system. But it turns out that all of them are either trivial or are differential consequences of the on the main equations. For example, if you consider the variational derivative of the coefficient 1, 3 with respect to u, then you will get this equation. This is a second-order equation, and it is a consequence of MKdV. If you differentiate this with respect to x, you will get this. If you consider variational derivative of L23 with respect to u, you will get again a second-order differential equation, and it is again a consequence of the previous two. If you differentiate this with respect to y and use the sine-Gordon, then this will be a consequence of the previous two equations. And the last one, non-trivial equation, it is the variational derivative of L23 with respect to ux, should be equal to 0. Then if you compute this, the result will be this differential equation. And this is again a differential consequence of sine-Gordon. If you differentiate sine-Gordon with respect to x, you will get exactly this equation. So you can safely omit everything else and say that the system of multi-time Euler-Lagrange equation is just consisting of the sine-Gordon equation itself and its symmetry, which is the potential MKdV. Now, how this is related to the classical theory. In the classical,
Sorry?
yes,
May I ask?
sure.
Yeah, how to define coefficients of the two form?
How do I find them?
Yeah.
I will explain this in a minute.
Okay, thank you.
Actually, they were found by using variational symmetries.
Okay.
But in the classical two-dimensional theory, like sine-Gordon, you start with a two-dimensional space-time with the fields, scalar-valued fields, and with the Lagrange function, which depends on arbitrary jet of u, actually on u and its arbitrary derivatives with respect to t1 and t2. You can think of them as x and y. And then the Euler-Lagrange equation is just vanishing of the variational derivative of L with respect to U, which is given by this formula. These are the derivatives with respect to T1 and T2 of the corresponding partial derivatives of L with the alternating signs. Then the Noether's definition of generalized vector field is now very simple. This is just a vector field in U with coefficients which can depend on higher order derivatives of U, arbitrary partial derivatives of U. So in this sense, it is not a usual vector field on R, because this function does not depend on U alone, but also on derivatives. And this generalized vector field can act actually on arbitrary differential polynomials of U, again, just by applying the same recipe for partial derivative of any function with respect to any partial derivative of UK is supplied by the differentiation of the coefficient V with respect to the corresponding times. Now, the Noether's definition of a variational symmetry. If you have an arbitrary Lagrangian in 2 dimensions and a generalized vector field with respect to 2 times T1 and T2, then the variational symmetry is characterized by the fact that the derivative of the Lagrange function with respect to the vector field is a full divergence. So is d1 of something plus d2 of something. And those two functions, f1, f2, they also can depend on partial derivatives of f1 of u with respect to t1 and t2, are called the flux of the variational symmetry. And what comes to replace the notion of integral of motion is, of course, the notion of a conservation law in the theory of PDEs. And the definition of the conservation law is of a conserved current of a conservation law. Say you have two functions, J1 and J2, and the full divergence of the pair J1, J2 should vanish, but now not identically, but on solutions of Euler-Lagrange equation. So, which means that we require that the full divergence of the conserved current is proportional to the variational derivative of L with respect to U, and the proportionality coefficient is called the characteristic of the conservation law. Now we are just dealing with one function, not with an n tuple of functions, but with one function, because we are considering scalar equations. But the variational derivative can depend on higher order derivatives. So the situation is simpler in one sense and more complicated in another sense. So the Noether theorem is again a one-to-one correspondence between variational symmetries and conservation laws. Suppose that you are given a variational symmetry of a Lagrange function L with a flux F. Then one can construct a pair of functions a1 and a2. I will give you the prescription on the next slide, such that the functions j1 given by these and j2 given by these constitute a conserved current of the Euler-Lagrange equation with the same characteristic V, which appears in the variational symmetry in the corresponding vector field. And conversely, if you start with a conserved current, with a conservation law for Euler-Lagrange equation, with a characteristic V, then this characteristic gives you a variational symmetry of the Lagrange function, and the flux of the variational symmetry is given by reading the same formulas for F. These are the same formulas. The proof of the Noether theorem is again a consequence of an algebraic identity, and the algebraic identity reads as follows. So the action of the generalized symmetry on the Lagrange function minus the characteristic of the generalized symmetry times the Euler-Lagrange expression times the variational derivative is a full divergence of something. So there exists function a1 and a2 such that this expression is given by d1 a1 plus d2 a2, or in other words, that this is a full divergence. And then the fact that this is a full divergence and the fact that the divergence of j1 and j2 is proportional to Euler-Lagrange expression are equivalent, provided you define or you relate the current and the flux by these formulas. The sum of the components of the current and the flux are just those two functions a1 and a2. So the proof of this theorem is trivial, provided you are able to express this thing as a full divergence of something. And this is complicated by straightforward computation. I will not go into the details of this computation. At the very end of this computation, you have this expression in terms of L, and this expression is manifestly a full divergence because you have here the derivative of something with respect to T1, derivative of something with respect to T2, and these can be distributed arbitrarily between the derivatives with respect to T1 and T2. Actually, it is either the derivative with respect to T1 of this expression or derivative with respect to T2 of this expression, or can be distributed with the coefficients 1/2 between the both. So the A1 and A2 are not defined uniquely, but only up to trivial divergences. Okay, and returning to the example and to Irina's question. So for the Lagrange function of the sine Gordon equation, so the Euler-Lagrange equation is computed to be the sine Gordon equation itself, and one knows, or one has known for a long time, that the potential KdV equation is a generalized symmetry. So if you take a generalized vector field with the function v, which is just the right-hand side of the potential KdV, then this generalized vector field is a variational symmetry for the sine Gordon equation. And one can compute the flux f1 and f2. These are just functions of u, ux, and uy, which are verified by a straightforward, not very short, but a straightforward computation to be the flux of this generalized symmetry. And moreover, of course, you can compute the conserved charge of this generalized symmetry. It is given by this simple formula. Now, again, we change the point of view from algebraic to geometric. So we now have a differential operator dv, which acts on functions of two variables, x and y. And we interpret the potential KdV as a flow of the space of solutions instead. So we now introduce, so to say, the third time t, and we consider functions of three variables, x, y, and t, and these functions satisfy sine Gordon equation with respect to xy variables and the compatible MKdV flow with respect to t and x variables. And then the prescription, which is maybe not obvious, but which works in this particular case and which answers Irina's question, is the following one. Coefficient L1 of the two form is just the Lagrange function L. Coefficient L13 of the form is obtained if you replace in the flux F2, in the flux component F2, the V, which is the right-hand side of the potential KdV, just by a formal expression UT. So let me return to the previous slide. Here is F2, and in this F2 you have the characteristic of the vector field V. You now replace this V by UT, and you get nothing but the coefficient L13 of the form, which only depends on UT and UX. And the same is the recipe for the coefficient L23. You replace the component Fy of the flux in the component Fy of the flux, the expression V, by the formal first order derivative Ut. So this is exactly the two form which I demonstrated you at the beginning of this section. And the claim is that if you compute the Euler-Lagrange equations, multi-time Euler-Lagrange equations for these two form in a three-dimensional space, then this system is compatible, and moreover, as we have seen, it coincides with the sine-Gordon equation plus the potential KdV equation, and it consists of those two equations and their differential consequences. So actually, there is one further remark. If you replace the corresponding generalized symmetry acting on the functions of xy only by the full derivative operator with respect to the third time, t3, now everything happens in a three-dimensional space-time, so with three times t1, t2, t3, or x, y, and t. Then what comes to replace the defining relation of the variational symmetry? I remind you that this is an algebraic identity. So here everything is an algebraic identity for functions of x and y. If you consider functions depending on x, y, and t, on t1, t2, and t3, and replace this operator by this operator, then the result will not be 0, but it will be 0 on solutions of multi-time Euler-Lagrange equations. Yeah? So the corresponding combination of the derivatives of L12, L23, and L13 is not identically 0 as a function of two variables, but is 0 on solutions of multi-time Euler-Lagrange equations. Actually, any one of them suffices. On solutions of the sine-Gordon equation and on solutions of the potential KdV equation, this expression is equals to 0, or in other words, the pluri-Lagrangian two form is closed on solutions of multi-time Euler-Lagrange equations, and this corresponds to commutativity of sine-Gordon equation with the generalized symmetry given by the potential KdV equation itself. Actually, I prepared also a couple of slides giving pluri-Lagrangian formulation and its relation to variational symmetries for the full KdV hierarchy, but I'm afraid that my time is now over, so I think that I will finish at this point, and
no problem. So this is flexible, so I'm happy that you explain in detail.
It's up to you. Okay, then let me to quick formulation of the results for the KdV hierarchy, for the whole KdV hierarchy. So you all know what the KdV hierarchy is. It is a system of PDEs with respect to the times T2, T3, and so on. And here are the right-hand sides of these PDEs. So these are the full x derivatives of those expressions called R. So the KdV equation will be time 2 derivative of u is equal to uxx plus 6 times uxu, and so on. So these are KdV equations in a divergence form. The fact that all of them are x derivatives allows to introduce the potential KdV hierarchy. So if you denote u by vx, then the v's are satisfying those differential equations. The g's are nothing but rk's of u or of vx. So this is the right-hand side of the potential KdV equation and the next equation of the hierarchy and so on. There are infinitely many. And I will also consider the so-called differentiated potential KdV hierarchy. It consists not of evolutionary equations, but of second-order differential equations, and they are obtained by differentiating those equations with respect to x. Just differentiate everything with respect to x, you will get f Vx differentiated with respect to the time number k is given by this expression. And those latter equations are Lagrangian in the classical sense. It is well known, with the Lagrange functions given by the following expressions. The kinetic energy is the product of Vx and the derivative of V with respect to the corresponding time. And the potential energy is given just by the functions hk, which are related to gk by this formula. So this is a classical thing, very well known. Now, what is probably less known, but is also a more or less classical, is that in this hierarchy, each equation, evolutionary equation, is a generalized variational symmetry for the corresponding differentiated Lagrangian system. So if you start with the differentiated system in the plane xti, so the KdV equation number I differentiated additionally with respect to x. So you start with such equation, like here, number I. Then the evolutionary equation number j again arbitrary, is its variational symmetry, which means that the generalized vector field with the right-hand side Gj acts on the Lagrangian of the equation number I, and the result is a full divergence. It's a sum of the full derivative with respect to x of something and a full derivative with respect to time number I acting on something. And moreover, one can say more about this something, namely this is the Lagrangian of the equation number j with the derivative Vtj replaced by the corresponding characteristic of the generalized vector field. And here it is really something, there exists a formula, but this formula is not nice. But one can prove that if you interchange the roles of I and j, then those densities can be seen as coming from one and the same differential polynomials depending on derivatives of v with respect to all three times, x, ti, and tj. So this expression only depends on the times number I and on the variable x, but it turns out that it comes from a more general expression depending on all three partial derivatives. And as a result, one finds the pluri-Lagrangian structure for the KdV hierarchy. Namely, it is the following two form. Here, the coefficients by the expressions dx wedge dti are just the usual, the classical Lagrangians, two-dimensional Lagrangians, which appeared already on the previous slide. And all the coefficients Lij, which were unknown in the classical theory, are defined as above. And they, of course, are absent from the general theory, but it turns out that the multi-time Euler-Lagrange equations for these pluri-Lagrangian two form is consisting just of the system of evolutionary equations, the first equations of the potential KdV hierarchy. And moreover, this form is closed on joint solutions of these equations. So this is actually all I wanted to tell you, and let me just give you a very short summary. So the pluri-Lagrangian structure for integrable systems is a Lagrangian analog of commutativity, of integrability. And it turns out to be very intimately and very closely related to a very classical subject like variational symmetries. And what is very remarkable that this recent symmetry appeared actually in the discrete context and is very natural and beautiful in the discrete context. But on the classical level, so the theory of variational symmetries is non-existent on the discrete level. And it is my proposal to try to reverse the relation between the classical and modern, and to try to obtain something in the classical area of variational symmetries in the discrete context, starting from the modern pluri-Lagrangian theory. Thank you very much for your attention.
Okay, thank you very much for very, very clear thoughts.
So I'm happy to